Hello world, welcome back to my channel. Now before I say anything, let's have a look at what's happening here. So this is our MSP430 launchpad, which has the G2553 microcontroller plugged into it. And here we can see an LED blinking at a specific rate. It's approximately 0.065 seconds. Now usually we use delay functions in software for blinking the LED, and that's also more often our first program. However, that isn't an efficient way to go about doing things because it keeps the CPU busy and consumes a lot of power unnecessarily. So what's the efficient way to get this thing done? That would be to use the timer peripheral, and that's what I have used for this program, and that's also the topic of discussion for today's video. But before we proceed, please hit the subscribe button and subscribe to the channel.
Alright, so we'll be covering the MSP430 timer in compare mode today. And timer peripheral is so vast that you cannot cover everything in one sitting. It'll require definitely more number of videos, and that's why a series will be presented to you. And this is the first part, which will deal with the compare mode. Let's just see what exactly is timer. So when we think about timer, you can think about something like an hourglass, except for it's much more sophisticated and much more flexible than an hourglass. But I think the basic example, if I want to give anything which is closely resembling a timer, then it'll be an hourglass. Let's see and understand timer in MSP430. Let's see the basics of that. So first of all, we've got something called as counter. Let's just call it counter register, which is 16-bit long. That means it can go from 0000H to FFFFH, which is from 0 to 65535. It can count from that to this value. And for that, it needs a clock, which is called as input clock. So at every rising edge of the input clock pulse, the counter counts. It increments or decrements. And for simple understanding, let's just assume that it simply increments. So at every rising edge of the clock pulse, you have the counter incrementing one by one. It counts from 0 to the final value. It counts till the final value. It overflows, and because of that, you get an interrupt, which is called as TAIFG. Now, what is TAIFG? It is basically timer A interrupt flag. What do we mean by that? We'll get into it again in a while. But just remember that it's an interrupt that you get because of the overflow that happens because of counting till the final value, and then further incrementation leads to overflow and thus an interrupt. So this is the basic idea of what a timer is in MSP430. Now, as you can see that it relies a lot on the input clock. And it does not do anything on its own. It's simply a counter which goes on incrementing, but it depends on the input clock. So the accuracy of the timer will depend on the accuracy of the input clock. The next is the compare mode. Now, what do we mean by this mode? So again, we've got the counter, which is 16-bit wide. We're feeding it the input clock. It counts from 0 to 65535. Then it overflows, and then we get the interrupt. Now let's just assume that I do not want to count till the final value of 65535. Instead, I want a value lower than that, but something different than that. So I can put that value in something called as compare register. Let's just say I want the value of 50,000. So I do not want to count till 65535. Instead, I want to count till 50,000. So the moment that count 50,000 is reached in the counter, the moment that is reached, you get an interrupt, which is called as CCIFG. Now, CCIFG stands for Capture Compare Mode Interrupt Flag. Now, we are not discussing the capture mode, so forget all about it right now. But we're discussing the compare mode. So this is the compare mode interrupt flag, which gets set the moment you have your counter value equals to the compare value. So that is the compare mode. In this case, you want a value which is less than but not equal to the final value, which is the 65535. You want something other than that, then you feed that value into the compare register. So you get a different time period. Now, let's look at the simplified structure of timer A. So MSP430 has got two types of timers, timer A and timer B, and G2553 has got timer A variant. So let's look at the simplified structure of that. Now we've covered the basics already, so it will be very simple to understand this now. So there's clock select. As we know that there's an input clock which is given to the timer. So this is the same clock that we are talking about, except that it has got 4 options. Rather than just one input clock, you can select from any of these 4. And for that, you've got something called as tassel bits, which is like you've got 2 bits to select which clock do you want. So if you want TACLK, which is timer A clock, it's an external clock. You can connect it externally. Or if you want auxiliary clock, which is ACLK, and for that, I think you need the 32 kilohertz crystal soldered onto your launchpad. Else you can go for SMCLK, which I have used for this particular program, which is 1 megahertz. Or you can go for inverted clock, which is, I think, TACLK, but inverted, again, external clock. So this multiplexer, that is clock select, allows you to select either of these 4 clock from either of these 4 clock options, and we've selected SMCLK. Now after selecting that, you can divide that clock further by 1, 2, 4 or 8. So it's a prescaler, and you can divide it using either of these values. I haven't divided it in our case, but what this does, it offers you like flexibility in terms of the frequencies that are available, and essentially it just slows down your clock basically and offers you more flexibility in terms of how many frequencies you have available with you. Then the next thing is TAR, which is the official name for your counter register that we just saw in the previous slides. So the counter register, which is the 16-bit register which increments or decrements with the rising edge of the clock signal. So that register is the timer A register, which we were talking about. So with each pulse, obviously it will increment or decrement. And then the moment it overflows, you get the TA-IFG interrupt. And also we know that in terms of compare mode, we also have got compare register, which officially is called TACCR0 register. And the moment the count becomes equal to TACCR0, that is the TAR value becomes equal to TACCR0, you get an interrupt. And that would be the CCI interrupt, which is your capture compare interrupt. So we can also clear the TAR using something called as TACLR bit. And the moment you clear the TAR, well, all the settings just vanish and then you have to start off again. Next is the modes of timer. Now, as we know that compare is one of the mode, so let's see what are the different modes which are available and what are the official names, basically, because we've already seen this before without knowing the names. So the first mode is continuous mode. So as the name itself says, continuous, that means it repeatedly counts from 0 to the final value, which is 65535. And so that's the first thing that we saw in the counter, because you have like 16-bit counter, so it can go naturally from 0 to FF 4 times FH. So that's the normal run, and that is called the continuous mode. Then the next is up mode. This is the mode that we have used for our program. And in this case, as you already have seen, there's a compare register that we've spoken about, which is TACCR0. So you can set the value anything other than the 65535 value, and you have your up mode set, and it repeatedly counts from 0 to that particular value. So that is your compare mode basically that we're talking about. Then the next is up down mode. That is also a kind of compare mode. In here, what you're doing is, again, you're setting a value which is again different than the 65535, and here also it counts repeatedly from 0 to TACCR0. But you can see that from TACCR0, it does not immediately go to 0. Rather, it runs backward, and from TACCR0 then goes to 0 in a sequential manner. So you can see that you get a symmetrical pulse instead of just like a straight line. And this again is used for symmetrical pulse width modulation. And that's your up-down mode. And the last mode is stop mode, wherein the timer is simply halted, that is stopped. All right. Now there are certain flags which are associated, that is certain interrupts which are associated with all these modes. So the first one is continuous mode. Now we've already discussed TAIFG. It occurs when the timer counts from the final value to 0. So in that transition, TAIFG occurs. That is when it drops from FF to 000. At that time, you get your TAIFG. Then in case of up mode, we know that there are two interrupts that occur. So the first is CCIFG, which is when your value goes from TACCR0 minus 1 to TACCR0. Between that transition, your CCIFG flag gets set. That is your capture compare interrupt, which is what we've used in our program as well. And then the second interrupt, which is TAIFG, which is normal in continuous mode, the same thing, except for in this case, you get it when the transition occurs from TACCR0 to 0. So in between that, you get this TAIFG interrupt. As you can clearly see, there's a difference of 1 cycle between CCIFG and TAIFG interrupt. Then the next is in case of up-down mode, we have CCIFG again, and it occurs when the count goes from TACCR0 minus 1 to TACCR0. At that time, you get the CCIFG flag. And the TAIFG flag is set when it goes from 0001 to 0000. So the moment it comes down to that value, when that transition happens, then at that time you get your TAIFG flag set. So there's a difference of half a time period between the CCIFG and TAIFG in case of up-down mode. So that's all about the interrupt flags. Now let's go ahead and see the other registers which are present in your MSP430 G2553 specifically. So this is the functional block diagram of your G2553 as it's given in the data sheet of your microcontroller. So here we have got two timers, and these both are timer A variants. As you can see, there is timer 0 and timer 1. Both of these are timer A variants. So there are two types of timers, timer A and timer B. But in case of G2553, we've only got timer A variants. And what do we mean by timer 0 underscore A3 and timer 1 underscore A3? So what does this 3 stand for? 3 stands for the 3 capture compare registers that you get with each of the time modules. So there's timer 0 and timer 1. In both of them, you've got 3 set of registers, capture compare registers. And CCR0 is already familiar. Now we know that it is used for setting different modes. None of the other registers decide the modes, but the CCR0 does. So that's something that we've already seen. There's also CCR1 and CCR2. So because of that, you get 3 channels. Then the next is timer A interrupts. So there are 2 interrupt vectors which are associated with 16-bit timer A module. Basically, you just get 2 vectors. And the first one is dedicated to TACCR0 CCIFG flag, which is your capture compare interrupt flag. That is something that we've used in our code as well. So we have used the TACCR0 interrupt vector for that purpose, and it's got the highest priority. And the next vector that we have is TAIV, and this is used for all the other CCIFG flags, that is your CCIFG 1 and 2 and all of that, and also for your TA, that is your timer A interrupt, which is your TAIFG basically. So TAIV is used for everything else. So because there's only one vector assigned to all the other flags, or rather all the other interrupts, we'll have to use a switch case. because we have to decipher which particular interrupt occurred. And there's also a TAIV register which keeps a count, basically, not particularly count, it's like it keeps a value in it to describe which particular interrupt has occurred. So depending on the value that is present in TAIV, you can have a switch case, which will then allow you to execute whichever function you want related to that particular flag. So if it is CCIFG1, then TAIV will have a particular value, and then you can write your switch case accordingly so that only the routine for CCIFG1 gets executed. Now, there has to be some relation between the time period and TACCR0 as well, because I am not going to feed the value directly. I would rather know the time period that I'm interested in. So let's understand the relation between the TACCR0 and time period. It's quite straightforward. So it is equal to F into T by D minus 1. So what are these things? So TACCR0 is obviously the time array capture compare register value that we want to feed in, which we do not have. F is the clock frequency in hertz, which we definitely know. So in our case, it's going to be 1 megahertz, for example. T is the delay or time period in seconds, which you are interested in having. So that's something that will be known to you. Next is D is the divider or the prescaler. And basically subtract 1 from this particular factor, that is F into T by D. This is to compensate for, you have like your timer running from 0 to 65535, which basically means that it has got 65536 ticks. So to compensate for that one particular tick, you are subtracting the value over here by 1. So that's the whole idea, and that's why that -1 comes into picture. So I hope you understand that, and I hope I made some sense. But let's see an example. So if you have like 5 milliseconds and you are using 1 megahertz clock, and let's say you do not want any divider, or rather you want to keep it as 1, in that case, you'll have to configure the timer in up mode with TACCR0 value as 4999, which simply means that you'll have 5000 ticks. And I hope that makes sense now, so that you can get 5 milliseconds. So that's the relationship that you have between your TACCR0 and time period. It's very important to know this as well before you start programming the register. Now let's look at the steps to program the time array. This is more of a summary rather than anything else, and also to know which register should be used for which setting, sort of a thing. So first of all, you have to use TACTL register. Now this is timer A control register. You have to configure this register, and what do we have to set in this register? So first of all, you have to select the clock. Now you remember the tassel bit over here, 2 bits for clock selection. So that is a part of TACTL register. So you select the clock here. Then you select the mode also over here. That is, the 4 modes that we had discussed earlier. So that selection is also possible in this register. Then you have to do some interrupt settings. Now TACTL is specifically used for your timer A interrupt. So the flag and the interrupt enabling is done over here. Reading of the flag and enabling the interrupt for your timer A, that is TAIFG, is done in the TACTL register. Now in our program, we're not using the TAIFG flag. So we're not doing any interrupt settings in this particular register. Then the next thing is configuring the capture compare register. So that is TACCR0 register. And there's also a TACCTL0 register, which is specifically for capture compare control. So there's a register for that as well. So let's see what configurations do we have to set. So the first thing is, because we are using the compare mode, the TACCR0 register will have a particular value. If it was capture mode, it will be something else. We don't want to get into that. But if it is compare mode, you have to specify the value. As we've seen, like 4999 is a particular value that you need to write in your TACCR0 register. Once you're done with that, in TACCTL0 register, you will have to set the interrupts. So because we are using the I interrupt. So that's why we need to enable that. And capture compare related settings are done in capture compare control register. So this interrupt will be set in TSCCTL0, and that's what we're using in our program. Then the next thing is interrupt flags should be cleared because we are programming the timer. You do not want the flags to be enabled by default, so you need to clear them up, and then you can start the timer. And you also need to have your ISRs in place. Next is always we have a software flowchart. So we stop the watchdog timer. Then I have used port 1 bit 6, which is the green LED, because I simply do not like the red LED. So we've used the green LED for the output, and then we enable CCIE, that is capture compare interrupt is enabled in your CCTL0 register, as we saw earlier in the steps. Then we set the count in TACCR0, and in this case I think we've used 0.065 seconds, so accordingly I think it's around 65,000 is the count that we've used in TACCR0. It's in up mode. Then we configure TACTL, which is timer A control register, wherein we've selected the clock as SMCLK and we've set it in up mode as well. And the next is we enable the low power mode and the global interrupts. And that's it. That's the end of it. Now, the moment it overflows, the timer ISR will get executed. And in that ISR, we are simply toggling, as we saw in the previous clip, that we were toggling the LED. So it starts blinking. So this is the whole idea. Also, the code is very simple, and it is available on my blog as usual. So whatever the code is there for whichever project, it'll always be there on my blog. So do check the link in the description below. In the future video, we'll look at the generation of PWM signals using timer. And if you have found this video helpful, then please like and share it. Also feel free to comment down below in case of queries or suggestions. Please do not forget to subscribe to the channel if you haven't already. And I'll see you next time. Bye world.